Hey guys, it's Sarthak from FTC Team 9794 Wizards.exe. And in this video, we're going to get into the software and algorithms you'll need for getting odometry up and running for you to use on the software side of things. So the first thing I'm going to do is I'm going to open up Android Studio, and you'll see that I have the newest version of the Skystone FTC SDK, version 5.2. If you've not yet downloaded the newest version of the FTC SDK from the GitHub repository, I would recommend doing that just before watching the rest of the video. And in fact, we released a great video a few weeks ago on using Git and GitHub to do just that. So I'd recommend checking that out if you haven't already watched it. Now, before we get started in Android Studio, we're going to have to download a couple files, which I prepared for you guys. These are three Java classes that are essential for using odometry. There's a calibration program. One of the Java classes contains the actual algorithm, and the other Java class is just a sample program to make sure everything's working. So what I'm going to do is I'm just going to go ahead and click on all three of these files, Control click, and I'm just going to download. Yep, there we go. Starting to download. I'm just going to download those files over there. So you should see that you got the zip file. When you head into your downloads folder, I'm just going to refresh. There you go. We have that. Just got to extract files. I'm just going to put them in my downloads folder again, and I'll copy and paste them into Android Studio in a moment. But you can go ahead and extract those files, and you'll see that it creates a folder over here. And now you should see three Java classes. So I'm just going to select all of those, copy them. Then I'm going to go into Android Studio and paste them. I'm going to make a new package first. I'm just going to call this odometry, just for some organization. But I'm going to paste my Java classes into here. Go ahead and press OK. And now you should see, I'm just going to add all these to Git. You should see three different Java classes right here. So the first one we're going to talk about is the one called Odometry Calibration. So why don't you go ahead and open that up. What this class does is, first of all, it's an FTC op mode, and it's very important to run this on your robot because by running this program, the robot will calculate and store the required information, and constants like how far the encoders apart from each other on the drive base, and the location of all three odometry encoders. And these are needed for the robot localization algorithm to run, which we'll get into in a minute. But before we download this code onto your robot, we're going to have to make a couple changes. So I tried my best to make sure this will work on all of your robots, but there are going to be some things that you have to change as it's too hard to predict what's going to be on what robot. So the first thing we're going to have to change is the hardware map names for all the drive motors and odometry wheels. So you can see that the default hardware map names are RF, RB, LF, LB for the respective drive motors. And then I've assigned the encoder names for the encoder hardware names based off the motor ports that they're plugged into. But again, this is going to change on each robot. So first, go ahead and update the hardware map configuration name you have for your four drive encoders. And then for the three encoders, so if you have that left encoder plugged into the same port where your right front drive motor is plugged into, you want to make sure those have the same hardware map name. So, so since that's the case on my robot, I have RF name equals RF, and then the vertical left encoder hardware map name is the same as the right front drive hardware map name. So I did that for each of my drive motors and each of my odometry encoders. And that's very important, otherwise your program will crash right away. So you want to make sure that's updated properly. And so I'm just going to quickly go through what happens in the code. But what the robot's going to do is it's going to use the IMU to pivot approximately 90 degrees. And what's going to happen is once the robot makes that pivot, it's going to record the data from each of the encoder wheels. And it's going to use that and just going to do some math calculations. And it's going to generate two constants. The first constant is the wheelbase separation, like I mentioned before. So how far the two odometry encoders that are pointing in the same direction, how far apart they are from each other in inches. And the second thing we're going to need is um, that third odometry encoder that's perpendicular in direction to the other two. We need to see how much it rotates, how many times it rotates, and how many encoder counts it picks up for each degree the robot rotates. Since if the robot turns, that third wheel is going to spin, and we don't want that value messing up our position. So we have to make sure we know how much it spins in that scenario. So we're just generating that value over here as well. So when you run the program, it's going to do that pivot. It'll take 1 second just to stop, take all the calculations. And then once it's done and all the values are written, um, it'll show you the position of the encoders, the raw positions, the angle of the IMU, and it's also going to display the two constants it generated and saved onto your phone. Now, what this does, it saves the text file. It saves two text files, each one containing the constant for the other, onto your local storage on your phone. So what's going to happen is those text files are generated, and each time you run the program using odometry, those text files are going to be read from. So it's important that if you swap out your phones or something, you might have to save these two files that are generated, or you just might have to run this calibration program once for each time you use your phones. Or if you use new phones or you factory reset your phones, you might have to run this calibration program a few times. So now, once you have changed these hardware map names up here for the the drive motors, and down over here on the line below for the encoders, one thing you should make sure is that also the IMU is configured properly. Just by default, it should be port 0 on your, sorry, I2C bus 0, port 0, and its name should be IMU in your rev hub. But you should just double check that just to make sure that everything is okay. And also make sure that you reverse the correct motors on your drivetrain over here so that your robot pivots 90 degrees in the fastest possible way. Um, that should be in the clockwise direction. So what we're going to go ahead and do is it should be ready to download. So you can go ahead and click that download button onto your robot controller phone. And in the next video clip, which is about 10 seconds long, you should see an example of the robot doing that pivot and showing the information it generates on the screen. So when you download this program and run it, it should be in the teleop menu, just a reminder, called Odometry System Calibration. But once you run that program, it should do something similar to what you see in the next video clip. So just make sure you watch for that. Okay, so hopefully your robot was able to run that calibration program just like it showed in the clip and store all of those values appropriately. So now that we have the constants we need for the robot localization algorithm to run, we should be able to get our algorithm ready. So what we can do is if we head into this global coordinate position, sorry, odometry global coordinate position Java class, we can start to take a look at what the algorithm looks like and just go over the basics of how it actually works. So I'm going to walk through the basics of the algorithm that computes the robot's global coordinate position in terms of x, y, and theta, theta being the orientation of the robot. And after that, we can go back into Android Studio and start creating some more programs. But first, I'm just going to walk through this real quick. So you can see that this implements runnable, and that's because this is a thread, a Java thread that runs in the background. That means that it's running concurrently with the rest of your op mode so that everything can update as fast as possible. Now over here we just have we have our encoders, some uh, variables to keep track of our position, the two algorithm constants that we needed, and you can see the files that they're stored in are over here. We have a constructor over here, which we'll get into more detail on how to use when we go over the sample program. And then now we have the actual algorithm. So I'm going to briefly explain the high level bits and pieces of the algorithm, just so you guys can gain an understanding. So I made just a quick little visual up here. So um, what we essentially have is we have a robot starting at one point and it's moving to another point in a very small amount of time. So in one loop cycle, which is typically sometime between um, 1/20th and 1/10th of a second, so 50 or 100 milliseconds, it's going to move from P naught to P prime. So it's moving from this position to that position. And over the course of that position, these two encoders on the wheels, on the left side and the right side, they have a change in value. So that's noted as delta S sub L and delta S sub R. And so what we see here is our robot's moving in kind of an arc direction. And the first step we need to figure out is the difference between, sorry, the average distance between the wheels. So we take the right encoder and the left encoder, add them together, and divide by 2 to get that average. Um, and what that average is used for, if we go back into Android Studio real quick, we calculate that average right over here. And this average, which the average is calculated right over here. Um, and this is used in future calculations. But the first thing that the robot needs to do is it needs to calculate the angle of change in that motion. So if we go back to our diagram, you can see that the robot started facing in this direction, 90 degrees. But then over here, it has some change in angle. So it has the original angle plus some change. And to calculate this, we just have to take the difference between the left and the right encoders and how much it changed, and divide it by that constant we calculated by running the calibration program, which is the robot encoder wheel distance. So again, how far those two encoder wheels that are facing in the same direction, how far apart they are from each other. And then what we can do is we can just add, so that calculates the change in the robot orientation, and we just add that variable to the variable that keeps track of the robot's orientation. One thing to notice is that this is in radians, not in degrees. The next thing we have to do is we have to figure out the components of the motion. So this means how much did the robot move in the x-axis and how much did the robot move in the y-axis. So what we have to do is we get the encoder wheel positions. So you can see we get it for the left encoder, the right encoder, and the encoder that's perpendicular to those first two. I'm just going to call it the normal encoder, normal for perpendicular. So we get how much those encoder values changed from the previous loop cycle. And so you can see before how we average those two left and right encoders. So that's stored in this value P over here. And N is just the change of that normal encoder wheel. And so what we can do is that since the loop cycles are so fast, we're assuming that the robot is moving in a succession of straight lines, an infinite number of straight lines basically. And if you're moving like that in a straight line, you have to have an x and y component, which forms a right triangle. And using that, we can find the difference in x and the change in x and the change in y. And to do that, we just do some basic trig over here, which I've shown over here. It's pretty simple, just right triangle trig. And then what happens there is we calculate the components for the x motion, and we calculate the components for the y motion. And then, so you can see this is the x motion right over here, and this is the y motion. And we add those to the previous x and y coordinates. So these these variables are constantly updating with the changes in each loop cycle to accumulate and calculate the robot's current position on the field. And then it quickly just stores some values that it's going to need for the next loop cycle, and it keeps running that over and over again. So you can see that when the thread runs, it just keeps calling this method to keep updating the robot's global coordinate position. So hopefully that all makes some level of sense to you, but basically we're just keeping track of how the robot is moving in very small motions and adding that all together to get the robot's coordinate position. So now I'm going to show the sample program that I've made for you guys just to test and make sure this works out. So what we see here is we have a couple we have our encoders, and we also have our hardware map names. Now, just like in the first part of the video series where we went over in the calibration program where we went over the hardware map names, you're going to have to change those hardware map names over here too if they are not already correct for your robot. So you can see we get the hardware map names, we reset the encoders. Now, an important step is that what we're going to do is we're going to have to reverse, essentially negate some of these. So I'm actually going to remove these lines for now. But what you'll want to do is, so when you press play, it's going to show you the X, Y, and orientation of the robot based on using that algorithm we had earlier, which is actually set up over here. This is where we create that thread to start updating the positions. But I'm going to add some lines into here where I'm going to show the raw positions of each encoder. So I'm just going to say vertical left encoder position, and then we have the vertical left dot get current position. And I'm going to want to do that for the 3 encoders. So we have vertical right, and then we have the horizontal encoder. So what you want to go ahead and do is you want to go ahead and download this program. It looks like there is an error. Sorry, we can just go ahead and delete this import statement and these two since they're not being used. What you can go ahead and do is download this program. Now, the first step when you run the program, what you're going to have to do is you're going to want to take a look at these 3 values. So what I want you to do is push your robot forward. So you want to push your robot forward and push your robot to the right. So it's moving in this direction basically. And since the robot moved forward and to the right, the vertical left, the vertical right, and the horizontal encoder, all 3 encoders should return a positive value. Now, if that doesn't happen, that's very easy to fix in the structure that's been here. So what you can do is if they're not positive, say they're negative values, which they shouldn't be, but if that's the case, we want to fix that. So what we can do is we can go in here and say global position update dot reverse, say it's the left encoder that was negative, you can say reverse left encoder. If it was the right encoder, we can go ahead and do that same thing, reverse right encoder. Same thing for the horizontal encoder, so you can call it the reverse normal encoder method. So if you push your robot manually, once you run the program, if you push your robot manually up and to the right, you should take a look at these values again. If any of these were negative, that means you have to reverse them. So, so you can reverse them using this line right over here. Now, one potential issue you may have with this is, say, you're an autonomous and you start programming your autonomous, and you have to reverse your two of your drive motors because of the orientation they're put in. So you have to reverse your left ones. Now, since I plug in, I plug in my vertical right encoder and my horizontal encoder into the left ports. But let's say that I have to reverse the left front and the left back drive motors, but the encoders are also mapped to the same location. This is automatically going to flip the sign on your encoder. So if that is the case, you may want to make sure that when you reverse your encoder, if you have to reverse a drive motor, check to make sure that encoder is not getting reversed. If the encoder is getting reversed, you either have to reverse the encoder or remove the statement that says the encoder is being reversed. So let's say I have to reverse my left my left drive motors, which are left front and left back. This means that since I also have the reverse statements over here, I'm double reversing it, which is just going to mean I'm going to get the wrong value. So I'm just going to go ahead and delete these values. And now the only thing that needs to be reversed is the left encoder. Now, again, I'm just speaking based off of theoretical robot, but you're going to want to make sure you update that for your own robot. So you're going to have to run this program, figure out which encoders you have to reverse. If you're reversing your left drive encoders, you want to make sure you're not double reversing any of the encoders as well. So what we can go ahead and do is just make sure you run this program, test that out, and make sure that you get the encoder positions correct, and make sure they're reversed in the proper way. And they're returning positive values when you push the robot up and to the right. So once you get all that fixed, so say you have the correct reverse statements in and everything's good to go in terms of the raw encoder values from these 3 lines, what you can do is re-download the program with the correct encoder settings. And then when you push the robot around, you should see the XY position and the orientation of the robot updating correctly, meaning that when the robot goes forward, meaning away from you, the Y position is getting positive, excuse me. And when it's coming to you, it's getting negative. When you push it to the right, the X value should be positive, and when you push it to your left, the X value should be negative. Um, so just make sure that is the case. It should be, but you should just make sure that is happening. And one thing to make sure is that you stop the thread when the program is not active. So once this while loop finishes. That wraps up the content for this video. Hopefully you were able to gain an understanding of how the algorithm works and how to set up the basic parameters you need for your robot. So you should have, by the end of this video, been able to run the odometry calibration program, understand the algorithm, at least the high level basics of it, and you should be able to run this sample program to first figure out how you have to reverse your your odometry encoders. And after you correctly reverse them and adjust them, you should be able to get the X, Y, and orientation and coordinate of your robot, which will always tell us where the robot is on the field, and we can use that information to move to specific locations on the field, which we will get into the next video in this series. But that concludes this video and all the contents in this video. Thank you guys for watching. If you have any questions about any of the steps in this video, or if you were confused about anything, please let us know in the comments, or you can also send us an email at wizards.exe@gmail.com. Please be sure to like the video and subscribe to our YouTube channel. And if you have any ideas for any other videos, be sure to let us know in the comments as well. We'll be releasing the next part of this video shortly, and stay on the lookout for any other videos we are releasing. Thank you guys for watching.